we know that DFT has a time periodic property. So if we consider the outside of the range, baseband range, how can you express it? Means that here we have xn. Then we will take DFT, endpoint DFT. Then we will have xk. Then if we take inverse DFT, then you will have time periodic signal in time domain. X tilde n. Actually, x tilde n, xn, the original signal is not same. When we consider only baseband interval from 0 to n minus 1, it will be exactly identical. But the outside of the interval, it will be duplicate. So we can express this term as x n plus r n in duplication and periodic. So the original signal is a periodic and time limited interval, but after DFT and again inverse DFT, then the result will be periodic signal. Here, if we put this as omega 1 hat k, omega 0 or 1 or anything else, what it looks like? Actually, it looks like Fourier series we already studied in chapter 3. That is the periodic signal in time domain is summation of harmonic signal. Harmonic means there is a fundamental frequency and multiplication, right? So we will study Fourier series in discrete frequency. So we call it discrete Fourier series. Here is a discrete Fourier series xn. To derive discrete Fourier series, we consider the result of IDFT. So x tilde is one of sigma xk exponential j omega j 2 pi k over n. When put this into here, xk over n, and we pull out the k, then it is something omega 0 hat or omega 1 hat. Now let's denote it. Like this, and 2 pi f0. Here we denote this is as ak. Then ak is xk over n. So from definition of DFT, it will be 1 of n sigma x, actually x n exponential j 2 pi k over n. Since it will be x tilde, it will be same for n is 0 to n minus 1. Only the difference happen when n is outside of this interval. So it is exchangeable when n is inside 0 to n minus 1. Okay, so we can denote. But usually when you consider Fourier series, they consider minus frequency. That means they consider from minus pi to pi, or from minus m to m. So we can change the variable to that. So we can change the variable from minus m to m. Instead of k, we can change it. So in the case of m is positive number, over 0, then it will be 1 over xm. And if it's negative number, can you consider this? There is from 0 to n minus 1. Then here will be minus m. X m minus m is the same as x m plus m and minus m due to periodicity. Like this. Okay. So it is m plus n when m is negative. So for real time domain signal, due to complex conjugate symmetry, so a minus m will be a complex conjugate of a m. And the case of discrete time, the summation is limited by m, and we have n point discrete Fourier series. So 2n plus 1 should be equal or less than n. Okay. We said a DFS is periodic, so we just match it. Fourier series we already studied. Fourier series handled periodic continuous time signal. What is the relationship between DFS, discrete Fourier series, and continuous time Fourier series? In continuous time Fourier series, from definition here is definition of Fourier series, but it is infinite number of exponentials spectrum. So if we have enough number of complex exponentials, then it can be enough when we studied in chapter 3. So here it will be we can limit the finite Fourier series from minus m to n. So we can handle this number in computers. We call f0 is fundamental frequency, and 2 pi f0 is denoted as omega 0 hat something, omega 0. Yes. So we can express as am exponential j 2 pi f0 mt. M is from minus m to m. So what will be the maximum frequency? It will be 2 maximum frequency will be 2 pi m f0 radian per second, or you can say that f0 hertz. To handle in computers the data, continuous time should be sampled. Okay, so let's consider sample the signal to get x tilde. So the rate will be fs. When you sample the signal in time domain, for recovery you should meet a satisfied sampling theorem. That means the Nyquist rate means 2 times of maximum of frequency. So fs should be greater than 2m f0. So let's sample to make x tilde and xn ts instead of a t. We put and ts, where one of s is a sampling rate, one of ts is a sampling rate. So when you consider here and f0 and ts, f0 and ts, we combine together. So we assume that here f0 ts is f0 over fs. We assume the ratio f0 over fs is 1 of n. Okay, so x tilde n is periodic with period n. So it becomes DFS. So let me summarize. So continuous time Fourier series and DFS. So we can use finite Fourier series and sampling at time domain, in time domain. Okay. Here is figures to explain. There is Fourier series xt, and it will be infinite number, maybe something like this actually. But first we consider only 2 plus m signal in frequency domains in the spectrum. And we sampling, and that is Fourier series, limited Fourier series, like here. So the finite Fourier series we used um, terms. First, we make a finite Fourier series like this, and second, sampling. Sampling means it will periodic in frequency domain. In time domain, sampling means periodic in frequency domain. When you sample in frequency domain, then time domain will be periodic. Okay, so when you sample at fs such that it will be greater than 2f0 due to a sampling theorem, so here will be duplicate, like we call it alias, every n here. And when we consider TFT, we move m minus m2 m is that n greater 0 to m minus 1. Then the relationship between the Fourier series coefficients and DFT will be 1 of xk will be n ak, n a0 n a n. Okay. We have studied Fourier series for continuous time periodic signal in chapter 3. Since continuous time cannot be handled in computer, so we sampled as a discrete time. So to study spectrum of discrete time signal, we study DTFT. The result of DTFT is continuous spectrum in frequency domain and periodic with period 2 pi. Since even if the signal is discrete in time domain, but the DTFT is continuous in frequency domain, so it cannot be handled in computer. So we sampled in frequency domain too with endpoint. So it is DFT. Fourier series, DTFT, DFT all needs full time. But actually in applications such like piano and music is change the frequency in time. Also our voice, my lecture in time, it is different. How can we analyze the time varying signal? So we consider window. We consider only limited time with enough information. We consider the frequency spectrum analysis. Let's call it time-dependent discrete Fourier transform. If there is no this point, it is 1, it will be same as DFT. But we considered limited number of time domain signal, and this is called window, time window. And window will change according to time, so like this. it will be moved. So sliding window we call it. And the spectrum, so the result from here, we call it spectrogram. That includes information of frequency and time together. Okay, there is functions in MATLAB, you can use it. For example, here it is Beethoven's Für Elise. Here is music. Music is function of time, also function of frequency. So with certain time window, we move like this and apply the DFT. So y-axis is frequency and x-axis is time. So here will be da 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 da, like here da 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 da. The others are noise like this. We can analyze the spectrum in time domain and frequency domain together. Let me show another example. That is one of my favorite songs, and it's sung by IU. And IU is very famous for her high pitch, three-level high pitch in Good Day. So we can analyze the her voice in the song. And the original song is among them. Let's remove the music recording part and let's analyze only her voice. After remove MR, here is a spectrogram I already used here. So the y-axis is time and y-axis is a frequency and the z-axis is power. So to make understood more easily, here is the y-axis is the time and frequency. So as you see here, three-level high pitches and very stable. She is a very good singer.